Imagine replacing an entire complicated circuit with just one voltage source and one resistor. No matter how complex the original network looks, the behavior seen by a load can often be reduced to this surprisingly simple model. In this video, you'll learn Thevenin Theorem, one of the most powerful simplification tools in circuit theory. Thevenin Theorem states that any linear two-terminal circuit can be replaced by an equivalent circuit consisting of a single voltage source in series with a single resistance. From the perspective of an external load connected to those terminals, the simplified equivalent behaves exactly like the original circuit. This theorem is extremely valuable because many practical circuits contain numerous sources and components that make direct analysis difficult. By replacing the entire network with a much simpler equivalent model, engineers can focus on how the load interacts with the circuit rather than repeatedly analyzing the complete system. The key idea is not that the internal circuit disappears physically, but that its external electrical behavior can be represented by a simpler model. As long as the load is connected at the same terminals, both circuits produce identical voltage-current relationships. A Thevenin equivalent is defined by two quantities, Thevenin voltage and Thevenin resistance. The Thevenin voltage is the open circuit voltage measured across the output terminals when no load is connected. This voltage represents the electrical potential available from the network. The Thevenin resistance represents the equivalent resistance seen when looking back into the circuit terminals. To calculate it, independent voltage sources are replaced by short circuits and independent current sources are replaced by open circuits. The resulting resistance viewed from the terminals becomes the Thevenin resistance. Once these two parameters are known, the entire original network can be represented by a simple voltage source connected in series with a resistor. This greatly reduces the complexity of future calculations involving different loads. Thevenin theorem works because linear circuits have predictable voltage-current relationships. From the viewpoint of a load, the only observable behavior is the relationship between terminal voltage and terminal current. If another circuit produces exactly the same relationship, the load cannot distinguish between them. Think of it like replacing the engine and transmission of a car with a black box. As long as pressing the accelerator produces the same speed response, a driver may not notice what is happening internally. The external behavior remains unchanged, even though the internal structure is completely different. Similarly, a load connected to a Thevenin equivalent experiences exactly the same electrical behavior as it would with the original network. The complexity is hidden inside a simpler mathematical representation. Engineers use Thevenin equivalents extensively when analyzing circuits with changing loads. Instead of solving the entire circuit every time a different load resistor is connected, they first determine the Thevenin model and then perform much simpler calculations. This approach is especially useful in power delivery systems, sensor interfaces, amplifier stages, and communication circuits. Whenever a subsystem interacts with another subsystem, engineers often represent one side using a Thevenin equivalent to simplify the analysis of the overall design. Simulation tools and circuit design software frequently use equivalent circuit concepts internally. Understanding Thevenin theorem, therefore, helps engineers not only solve textbook problems, but also interpret practical engineering models and design methodologies. Although Thevenin theorem is introduced in basic circuit theory, its influence extends into RF engineering. Many RF circuits are analyzed using equivalent models that simplify complex networks into manageable forms. Understanding these simplifications begins with Thevenin concepts. In RF systems, engineers often focus on source impedance, load impedance, and power transfer between stages. Thevenin equivalents provide a convenient way to represent signal sources and understand how they interact with amplifiers, filters, and transmission lines. As systems become more advanced, equivalent circuit thinking becomes increasingly important. Thevenin theorem teaches engineers to focus on observable behavior rather than unnecessary internal complexity, a mindset that remains valuable throughout RF and microwave engineering. So today, we learned that Thevenin theorem allows a complex linear circuit to be replaced by a single voltage source and a single resistance without changing its behavior at the output terminals. This powerful simplification technique makes circuit analysis faster, clearer, and more intuitive. In the next lesson, we'll explore Norton theorem and discover another equivalent circuit representation that uses a current source instead of a voltage source. If you found this useful, like the video, subscribe, and follow for the next lesson.